Well, I had a discussion with our rep from Metro Parks. Good news. Since we have a memorandum of understanding with them, and since we have our own insurance, we are covered, and none of our outreach volunteers need to sign a waiver to get to do outreach events at any of the metro parks. So that's really good news. I asked them, well, what about other members of other clubs? They're like, well, if they want to sign a memorandum of understanding with us and get their own insurance, that's fine. Otherwise, they can be covered under yours as guests since you're going to be hosting the event. But their lawyers agreed. The wording of the waiver was vague and wouldn't stand up in court. And since we had insurance anyway, so this is a very good thing. Let's see, what else do I have in the president's report that I can't get to because of the internet? Sorry. I'm going to have Dale Teamy sorry, not Dale Parton do his first VP report. While he's doing that, I'm going to try to get on the internet here so I can get my agenda.
Hi, everyone. Is this, sorry. Okay. I'm always looking for more speakers. Please don't be shy. Okay. If you have an idea, you can have an idea for something you would be interested in talking about 6 months from now, and I'd be delighted to hear about it. Or if there's a topic you really wish we would have a speaker on, let me know and we can try to find a speaker. So that's one thing to say. Another thing to say is our next meeting on the third Thursday of this month, which I believe is March 16, we are finally moving back to Macomb Community College South Campus for that meeting. It will also be online like this meeting is, but some people really like to go in person like me. So we will be there and we will be in the E building, not in the library that we sometimes used to meet in there on the South Campus. There's a map that was published in this latest WASP that just came out showing you how to find the right building. And the speaker for that meeting, the main speaker, will be Adrian Bradley. Something about searching for dark skies. Okay, any questions? Okay, hope to see you at Macomb. Cheers.
Okay, our second VP and observatory chair is currently on a plane, so we won't be getting a report from him. Treasurer Adrian is also not here, so the treasurer report is in the WASP, so continuing on that. Dale Teamy.
Yeah.
Publications.
Well, as Dale Parton pointed out, the WASP is online, and you can get the map to the Macomb location out from there. That concludes my report.
Oh. Okay. Yeah. And since my PC is running this, I need some power. Thing dying in the middle of the meeting. There we go. Outreach. Kevin, give a report really quick.
Sure. Mark Kedzier did an outreach event at the Warren Civic Library. He had about 20 adults and 15 kids. He had his 8-inch job there along with the library. telescopes, and he's helping them do some work getting 3 telescopes that they got via NASA grant, so that they could be checked out. And I've been talking with Monica Rittner at the Macomb Discovery Center. They need some help curating their programs, and I'm going to be getting more information on that. That's all.
Yeah, the Discovery Center was interesting. Diane and I went and talked with them about a week before COVID hit, and they did want us to partner with them, do a whole bunch of things. They were going to have some events outside in Macomb. They wanted telescopes and stuff, and then COVID hit, and the whole thing fell apart. So unfortunate. So I'm really glad that they need some help. Now that I have my agenda here. Okay, are there any first timers here? We have a first timer. Hi there.
I am, yes.
We generally have a handout with our information, but do we have those here? We need to get some of those things. We'll get you a handout. Oh, thanks for showing up.
Thank you.
You were the one who was interested in doing the computer. Hi, I need to talk with you on the break. Definitely. So our next meeting is going to be Thursday, March 18th. Dale already covered that, in person at Macomb. Thank goodness. Okay, so special interest groups. Let's start with David Levy. Can't hear you, David. Same problem I had. Mike's not on. David, can't hear you. Is he muted? He's not muted. You had my problem. I have like 5 microphones available for this thing. David, you there? Still can't hear you. Well, tell you what, while David's getting that, we'll go on to solar. Marty, tell him about the sun.
Still can't hear me.
Oh, there's David. There's David.
So I think
Can
you
you
hear
hear
me.
Yes.
Great. Okay. I just wanted to, sorry that I took so much time setting up the sound on this thing, but here I am. And I'm looking forward to the meeting tonight and to the one on a couple of Thursdays from now. For my quotation tonight, I've been observing the sun a lot. And today there are 7 sunspot groups. So we've got a heck of an active cycle going on. Anyway, for my quotation tonight, I'd like to quote Wendy's favorite. She always loved this very much. And this is from the Song of Honor by Ralph Hudson, the very end. I stood and stared. The sky was lit. The sky was stars all over it. I stood, I knew not why, without a wish, without a will. I stood upon that silent hill and stared into the sky until my eyes were blind with stars. And still I stared into the sky. Thank you for your patience, Bob, and back to you.
Thank you, David. All right, Solar Marty.
Well, the sun has been looking pretty spectacular lately, spots all over the place. I've been using binoculars made for looking at the sun, and pretty easy to see a good half dozen spots on the sun, moderate size. Once in a while, maybe once a month or so, there is a much bigger sunspot and sunspot group on the sun. Pretty active, lots of flares. There's been some aurora reported a week ago or so. Major auroral storm, even seen down in, not that it came from the north, but it was also seen in the southern hemisphere too. Australia reporting they're seeing aurora during that big storm, and all over northern U.S. too. So keep looking out and for the sun, lots of spots, flares, everything's coming up. It's all looking good.
I'll get some pictures from the Solar Dynamics Observatory at the break, but as Marty said, a lot of flares. I have an app on this thing, and it alerts me to solar flares, and I'll be sitting there working, and my phone will beep. I'm like, oh, another flare happening all the time. Double star, Riyadh. Did we see anything at all at the last observatory run?
We've been clouded out the last 2 times, but we'll be there again. We'll try again. Yeah. So the next open house is on the 25th, starting at 7:30. We'll be there. I'll have a list of double stars that we could start observing, and we still want to experiment with the spectrometer. So if you're there, hopefully it clears up, and we'll have a lot of stuff to do.
Hopefully we'll have clear skies.
Thank you.
We have somebody here who would like to restart our computers and technology special interest group. I will murder your name. So can you tell us your name? Vichalia? Vichalia. Okay, so anyway, well, if you're interested in computers and technology, talk with her at the break, and we will hopefully have a new special interest group that we'll be able to discuss the next time we're here. Well, that's fantastic. All right, do we have any astronomy questions from the members of the audience? 'Cause we rarely take them. Anyone? No? All right. So, any astronomy news? Anybody seen any interesting astronomy news? Well, we really need to start that back up again. Usually there's a lot of it. Well, I said my mother-in-law was watching something today. She's always watching astronomy things, how the universe works and stuff, and they were talking about Saturn and its moons and all the discoveries that Cassini made. That's just awesome.
I have a very humble astronomy observation to make. A few nights ago, I remember what night it was, there was a conjunction between Venus and Jupiter. It wasn't a super close conjunction, but it was just dazzling. They were so bright. It was spectacular.
Yeah, I call those accident causers. So it is 7:45 or close enough. Observing reports, and this is typically when some of our astronomers, our astrophotographers like to show what they've done. Although I don't think Adrian's going to be here tonight. So anybody have any observing reports? Go ahead and take the floor. Oh, come on. What you got? Which guy you've been imaging? That's Doug, right? That's Doug Bach. He's been imaging Comet 202283. And you can still see that? Any tail still, or is he just coma? The tail the whole time. How much longer? That should be that's leaving. That's on the way out. It's not gonna be around much longer. There is, if you're using Stellarium, there is a new version of Stellarium that came out a couple weeks ago. So I'll update that. They've added a whole bunch of new sky cultures in there, which is really cool. I would actually like to see someone do a report on all the different sky cultures inside Stellarium. They've added some cultures I have never even heard of, and that's interesting. They actually won an award for that like last year. So, no other observing reports. Well, do you want to do the short presentation early, Dale? All righty, let's go on to our short presentation. Our first Vice President, Dale Parton, will introduce our speaker of the night.
How is he going to get set up?
How is he going to get set up? That's a good question. Not on this, no. How are we gonna do that?
If he logged in.
Yeah, can you log into WebEx? Can you, yeah, do you have the email? Okay, if you can log into WebEx, that would be perfect.
Well,
That's been a pain in our side for a while there.
okay, people are working on getting John connected here. So while they're doing that, let me say our speaker tonight is John Dumar. He moved to Michigan in 1982, which is what, 40 some years ago, after graduating from Concordia College in Nebraska. And for the last 40 years, has been a physics and mathematics teacher at Lutheran North High School in McComb, Michigan. John then earned a Master of Education, Science Education at Wayne State, 1996. He coached wrestling for 24 years, was also a professional archer. He actually taught calculus and physics and wrestling to one of my sons. And he's a professional archer. When you start your talk, can you briefly tell us what does a professional archer do? I don't know. In 2015, he began his journey as an amateur astronomer and has not looked back. You ready to go, John?
I think so.
Maybe you ought to put your computer up here. So you can, okay.
I can, share this.
Well, thank you. A professional archer shoots arrows for money. That's what he does. I don't get paid much. I don't win much, but I have a few national titles, so that's it. That's pretty good. This one does? Okay. Okay. That. And I need to share my PowerPoint here. So I need to share my screen. Screen one. All right. Let's see. How can I see my presentation? Oh, you know what? I'm not on any other computer, am I?
We need to allow you to share.
I'm sharing.
You are.
I believe I am. Maybe I'm not. I'm not sharing, am I?
No.
Okay. It's not cursor. Cursor's gone. Oh, cursor went away. All right. You see it?
Yep.
Okay. Yeah, it got white. Let's see. All right.
All right.
All right. I'm very honored to be here to talk about the Laplace resonance. I got involved with this. I took data for images of the moons around Jupiter, and I've gone a little bit further into it, and it's very exciting information, I think. What we're going to do, we're going to take a look at what is resonance in the first place. What is that? Who was Pierre-Simon Laplace? And then what is the Laplace resonance? And what do the mean motions of the three inner motions suggest about the orbits? I'll talk about what mean motion means. And then really how should we view the orbits around Jupiter? Some terms, the Galilean moons, Io is the closest to Jupiter, followed by Europa, Ganymede, and Callisto. A resonance, a phenomenon in which a vibrating system is driven by another system to oscillate with greater amplitudes at certain frequencies. The mean motion means is another name for average angular velocity of a planetary body, planet or moon. You take the 360 degrees and divide by the number of days of the orbit, and it's assumed that it's a true circle, and you get what's called the mean motion in degrees per day. Perijove, the closest approach to Jupiter that the moon will get in its elliptical orbit, and apogee is the furthest that the moon will be in its elliptical orbit. So you'll see those words. I'll use those words along the talk here. I'm going to mute these, and then I'm going to put them on loop so they can keep playing. There we go. All right, so going clockwise in the top there, if you push on a swing and at the right frequency, the amplitude will increase. You get higher and higher. We say that we're in resonance with the natural frequency of the swing. The metronomes, they were set in motion at different times, so they're a little they're out of phase. But you see that the block of wood is shifting back and forth on some looks like cans of pop, and eventually the metronomes are now in sync. That's pretty cool. The bottom right is a set of pendulums. The outer pendulums have the same length, therefore have the same period of motion. So they have the same natural frequency. So when you set one of them in motion, you lift one up and let it go. The energy can transfer to that one on the left, but not the one in the middle. Its frequency is wrong. It's not the same or a multiple of the other. And then the Tacoma Narrows Bridge, if you're familiar with that, it collapsed in 1940. And during not a windstorm, just regular winds. If you ever row a boat, sometimes you see a little swirl of water on the paddle. So the wind will actually form these swirls of air, and they would push on the bridge. And they would push on the bridge and then release to go downstream, and more would form. And they would break off at the same frequency as the natural frequency of the bridge, and eventually the Tacoma Narrows Bridge collapsed. So resonance can be a cool thing, it could be a very catastrophic thing. Pierre-Simon Laplace was born in Normandy, France, 1749, 22 years after Newton died. He studied theology at the University of Caen for 2 years, age 16. There was notice that he was very good at mathematics, so he was encouraged to take up mathematics at the military school in Paris, where he also became a professor, 22 years old. He's known as the Newton of France. I'd like to be called the Newton of Michigan. That'd be kind of cool. He did a lot of different things. One thing, it was thought that Jupiter its orbit was collapsing and Saturn was expanding. And he showed that the mean motion of the two planets was invariable and the system is stable. I developed a nebular hypothesis of the formation of the solar system, the incandescent gases forming the planets and moons around the planets. In about 1800, he discovered the 421 mean motion resonance of the three inner moons of the Galilean moons. The periods of the moons were even measured by Galileo, but he suggested that as the cloud coalesced around Jupiter, that the moons moved into this 421 mean motion resonance. So what is this mean motion resonance? Here it is. You can get this at, on Wikipedia. The moons are moving around, Io's in the middle, or these closest, and Europa, Ganymede on the outside. I don't know if I can stop this without stopping the presentation, but you can see that when Io and Europa meet, Ganymede is perpendicular to that motion. And when Europa and Ganymede meet, Io is 180 degrees on the other side, and when Europa and Ganymede meet, Io's on the other side, 180 degrees, and Europa is 180 degrees when Io and Ganymede meet. So every time that Io goes around 2 times, Europa goes around once. Every time that Io goes around 4 times, Ganymede goes around once. And every time Europa goes around 2 times, Ganymede goes around once. So it's a 4-to-1 ratio of the orbits. And this is the mean motion resonance. If the animation is accurate, it should be an exactly 4-to-1 ratio. You take a look at the third column on the mean motion, it looks pretty good. 2 times 50 is 101, about 100, and 2 times 100 is about 200. It looks like it's pretty close, but it's not quite 4-to-1. It's a little bit more. And so if the ratio of these periods are what they are, shouldn't the moons get behind? And so the blue dots are where we start here. Io meets Europa, and Ganymede is at a right angle to the motion, or to the orbits. And if this is correct, then in 20 orbits of Io, Ganymede would go around 5 times. And the motion is, if you divide 203.489 by 4, you get about 50.9. But Ganymede goes a little slower. So it'd be about 20 degrees behind after 5 orbits. And then after 10 orbits, 40 degrees. So what's really going on? What's really happening? Where is this 4-to-1 ratio? And here's another animation. If you watch the hatch marks are the perijove of Io, Europa, and Ganymede. And if you watch the hatch marks here closely, and right now it's going kind of slow, but the hatch marks for Io and Europa are rotating. They're rotating clockwise as the moons are moving counterclockwise. And so the perijove, the hatch marks are the perijove, are rotating about 487 days for that orbit. It's precessing around Jupiter. But if you look closely, when Europa and Io meet, Ganymede is at right angles. When Europa and Ganymede meet, Io is 180 degrees on the other side. And when Europa and Ganymede meet, Io is 180 degrees on the other side. So it's the same situation as with the other animation, but here we have a 4-to-1 ratio instead of the 4.044, but almost perfectly a 4-to-1 ratio. So you need to view the orbits from the point of view of Io's perijove. I thought those were very interesting. So it isn't enough to divide the periods to see the Laplace resonance. We need to view the orbits from the point of view of the drifting perijove of Io, and the perijove of Europa follows along, and Ganymede is still. It doesn't move at all. I would in November of 2020, I did a presentation on Kepler's law that I was doing, collecting data to verify that law, and in that data is the this drifting perijove seen in the data. So that was very exciting to see that, and wanted to share that with you all too. But I, the quote here by Johannes Kepler is quite, it touches me very closely here. We ought not to ask why the human mind troubles to fathom the secrets of the universe. The diversity of the phenomena of nature is so great, and the treasures hidden in the sky so rich, precisely in order that the human mind shall never be lacking in fresh nourishment. I started gathering data to verify Kepler's law, and it just takes me deeper and deeper. So, thank you. Any questions? I could go back now that I've not shared it anymore. Yeah. Which one do you wanna? This one? Yes. Correct. That's right. Yeah, right. Oh, yeah, the perijove of Io and Europa rotate together. And when Io meets Europa, Io's at perijove and Europa's at apogee all the time. Yes. Yeah, have they found any animations of or modeling that shows the coalition of the moons moving into this orbit? I have not. No. Uh, it was mentioned that that the resonance were placed in or you were that put to music, and it's quite nice to listen to it as a comment. So yeah,
Music of the spheres.
Yes, indeed, music of the spheres, or like I like to say, fun with gravity. There's so many interesting things going on with gravity. All right, our main presentation is going to start at 8:30 or about 8:20. Let's take a 20-minute break, but give us a little extra time to get to the red code at the end here, and reconvene in 20 minutes for our main presentation. For everyone here, there are munchies available. We'll ask you to put $1 in there and get a pop and a munchie, or what are we asking? Help yourself. If you want to make a donation, but donations welcome. All right, so take a break, reconvene at 8:20. See you then. I'm gonna be sharing the sun here on the Solar Dynamics Observatory for the next few minutes. Hi, everyone. Welcome back. We're getting ready for our main presentation here. Our first Vice President, Dale Parton, will be giving you information on our speaker. Here you go.
Okay, sorry, we're a couple minutes late getting started. We got so involved in conversations here. So our main speaker is Adam Crowl. He's an Australian, and he's in Australia right now. I don't know what time it is there. The morning, okay. He is a space enthusiast, an independent researcher who unintentionally became an interstellar propulsion expert, space and science blogger, interstellar practitioner for the Institute of Interstellar Studies, and former member of Project Icarus. Is that how you say it? Icarus.
Icarus. Yeah.
Okay. He's been to the USA twice for interstellar events and hopes to visit again someday. His topic for tonight is kind of cryptic sounding: NERVA, Orion, and Now. Adam, you're on. You can share your
Thanks,
screen.
Bob. Oh, can everyone hear me okay?
What? What?
Can you hear me all right?
Yes, we can hear you.
Oh, excellent. Okay. WebEx isn't my usual tool of choice, so bear with me while I get it going. Okay. So, NERVA, Orion, and Now. I'll start with a picture.
Are you sharing? Or you're not sharing your screen right now?
Yeah, no, I'm about to. Okay. Right. Let's see. That's the one. Just bear with me. Okay. I will. Oh, it's the button. Okay. Well, hopefully you can see what I'm seeing. Sorry. So this is the recently proposed collaboration between NASA and the
Your
Defense
presenter view
Space.
right now.
Sorry?
We're seeing the presenter view.
Oh no. Okay. Show active. Okay. Oh no, it says it's streaming to YouTube. Sorry. Not quite sure how to flip between them.
We can go with this if that's okay.
Oh, sorry. Just hang on. I'll just stop sharing for a moment. I know meeting controls, right. Are you seeing it? Oh, it's still showing as me.
You're okay. That's fine. We can go with this.
Oh, just my audio. Oh, well. Hang on.
We can see it.
Oh, you can see the.
Yeah, we can see the PowerPoint, but with not presenter view, but the developer view, whatever.
Oh, okay. Righto. Okay. No, I just wish I could see what you guys are seeing, just so I'm a bit more confident about it. Right, so what you're looking at is aside from my ugly mug, is basically a schematic of artist's impression of a nuclear rocket that NASA and DARPA have agreed to develop over the next few years. They're hoping for a launch or test on orbit in 2027, which is only a few years away, but it builds on about almost 80 years of technical and engineering development. So with this presentation, I just want to explore some of the background history. Now, so yes, if they pull it off, the demonstration rocket for agile cislunar operations will be quite an achievement. But the beginnings of atomic rockets is a lot further back. Basically, at the end of the 19th century, when radioactivity was first discovered, people started speculating about using it for propulsion. So, and of course, fiction writers got on the bandwagon. One of the more interesting early concepts which used uranium is the flying ring from the tale, The Moon Maker. I'll bring up a picture. So, circular spacecraft with a directable block of uranium, which produces a beam of alpha particles. The tale was written in 1916, and it's fairly representative of what people were imagining atomic propulsion would look like. And it's actually written by a physicist, so it wasn't too bad for the time. In the 20s and 30s, plenty of people in the wake of Einstein started speculating about the conversion of mass into energy, thanks to the infamous equation E equals mc squared. But at that point, no one really had a clear idea of how it could be done. Astrophysicists had long been arguing that the sun had to be powered by some sort of nuclear reaction, because the lifespan that gravitational contraction, for example, was too short. So one of the speculations at the time was that the sun was somehow undergoing nuclear transformations. And knowledgeable science fiction writers picked up on that. One early example is John Campbell, who was trained as a physicist before he became a science fiction writer and then editor of Astounding / analog science fiction. So the first real breakthrough, though, was when Hans Bethe determined that the details of what's called the carbon, nitrogen, oxygen cycle, basically a series of fusion reactions which ultimately produce a helium atom and an excited carbon, which, as we know today, powers the sun by about 1.5%. The rest of it is a reaction that took a little bit longer to determine, and that's the very slow reaction between protons inside the cores of stars, which makes deuterium, which then itself fuses very easily. So in that same heyday of nuclear physics, other physicists were working out that there was another kind of reaction which caused accelerated nuclear decay, or what we call nuclear fission. And the details of that were also worked out in the 1930s. And of course, with the climate at the time, in the wake of the Great Depression and the looming European war, yes, things culminated in Trinity. So July 16, 1945 was basically the birth of the modern world, as we all know. And it's when the details of nuclear power just started to become known amongst the engineers of the US military, some of whom began speculating on what could be done to couple nuclear energy to powering rockets. So in the wake of that, there was studies of, for example, a very influential RAND study, which looked at a world circling satellite which ran from 1946 to 47. Yeah, and ultimately produced the space program, although there were a few false starts along the way. But as usual, science fiction writers got in on the act. Robert Heinlein was one of the earliest because he knew some of the engineers in the know. And he produced this classic, Rocket Ship Galileo, which was optioned for the movies and became the much beloved Destination Moon. Now, the technical details of the good ship Luna were as precise as they could be. For example, Heinlein was fond of using a very specific mass ratio for rockets, the one at which the amount of energy for a given delta V or speed change was minimized, which is important when you're adding energy to your rocket propellant. That mass ratio is about 5. So structure and payload, if we call that 1, and then you have to have about 4 times the amount of propellant, which in a nuclear rocket is effectively inert, although there are variations which actually use fuel embedded in the propellant. So moving on, there was all the serious work, such as the RAND satellite vehicle, which was a chemical rocket, but as part of the study, they looked at using radioisotopic batteries to power the system. The radioactive material of choice at the time was strontium, thus a radioactive strontium cell was considered. And I was trying to get a good picture of the next one, which was a nuclear-powered V2 rocket. Unfortunately, I didn't get it back from my source in time for this presentation, but if you imagine it being wrapped in insulation and looking like a standard V2, with the rather horrifying payload of a very large early atomic bomb. And of course, next notable mention is the Belgian comic strip artist Hergé and his moonship, which very similar to the good ship Luna, but had the much better concept for landing and launching using chemical rockets before the atomic engine kicked in. So, as good as it looked in fiction, the serious study at the time was quite extensive. There was a series of very influential papers written by an engineer and physicist in the Journal of the British Interplanetary Society, which produced this concept which basically a moon ship using a nuclear reactor, but launched on its way with chemical propulsion. But their papers sort of set the agenda for the next 30 years. However, in the very early 1950s, there were heavy criticism of some of the key concepts of nuclear propulsion. But fortunately, a young nuclear engineer, Robert Bassard, published in 1953 a landmark study which set the agenda for the work of the next decade, which was NERVA. NERVA stands for the Nuclear Engine for Rocket Vehicle Applications, and it was a joint NASA AEC experimental program. As you can see by this summary, there were quite a few test articles along the way, and it finished in the early 70s due to the budget cuts across the board that were essentially decimating most NASA programs at the time. But the work had progressed to the point where they were reasonably confident of being able to build a flight-ready nuclear propulsion system. So I want to explore NERVA a bit more. As you can see, there were multiple test reactors, the Kiwi series, Phoebus, which is a very large system, and then the NERVA specific test reactors. To see what those look like, so this is the basic concept for NERVA. There's a little video online, which hopefully I'll be able to share. It's on the Internet Archive, and it summarizes a lot of the work, but the actual operation of the NERVA core system is something that I wanted to show. Okay, so I'll try to share that with you all. Just bear with me. Okay. That's what I was doing wrong. I was sharing programs instead of screens. Sorry. Okay. So this is one of the control rooms in the NERVA test program. As you can see, the exhaust is venting directly into the desert sky.
We're not hearing any audio from the video you're showing. Is there any audio for that?
Oh, sorry. I wasn't sure the audio was going through, actually. Was it silent the whole time?
Yeah, unfortunately.
Oh, no. Okay. Well, sorry about that. Okay. So the main part that I wanted to look at is the explanation of how it works. So this is okay, hopefully you can see my mouse pointer. This is the main core, which is composed of graphite impregnated with uranium-235. The channels that you can see are coated in niobium carbide so that the hot hydrogen doesn't react with the graphite. Around it is the neutron reflector, which is made of beryllium oxide, which anyone who's worked with beryllium would get nightmares. But and to control the actual reaction rate itself, we have rotating control rods, one side of which is beryllium, which reflects the neutrons back into the core. The other side is boron, which absorbs neutrons and thus slows down the reaction rate. So when the boron side is facing the core, the reactors will actually slow down the rate of nuclear fission. So the whole system itself is self-pumping. So liquid hydrogen goes into the rocket bell here, and then through the outer part of the core to then flow back and get heated up and be vented through the nozzle. In any rocket, the nozzle is the chief working part of it, in that it changes raw heat and molecules in motion randomly. It gives them direction. So it's the basic principle of the Laval nozzle, something that's been known since the 19th century. So yeah, that's roughly NERVA in summary. I'm sorry I didn't have any audio on that one, because I could hear it just fine at my end. So I'll stop sharing that screen. Go back to hopefully sharing my Word. Okay. I'll share it like this. Okay. So here's the basic engine cycle. Works roughly as I described.
Oh, we're not seeing your share right now.
Sorry?
We're not seeing your shared screen.
Oh, really? Oh, okay. Okay.
There we go.
Yep. Okay. Right. For some reason, it doesn't like me trying to share between my monitors. So yeah, here's the basic engine cycle. Liquid hydrogen is the preferred propellant for high performance uses. The turbo pumps that maintain the pressure of the hydrogen feed into the reactor are powered by hot hydrogen. So that in itself was quite an engineering challenge, which the NERVA guys managed to pull off. Now, a fun appearance in more recent context is NERVA in Apple's alternative history series For All Mankind. Unlike the tests in the Nevada desert, NERVA is tested on the fictional moon base of Jonestown in the show, which if you haven't seen it, I absolutely recommend. It's quite the alternative history. So yeah, more test pictures, which you hope that there wasn't terribly much radioactive material in the jet stream, but who knows? And how they got the rigs out to the test stand was, of course, a purpose-built railroad. And to test what would happen in case of a major radiological event, they deliberately blew up one of the reactors. Surprisingly, the spread and the damage wasn't that much, so they were fairly confident it was a relatively safe system. So yeah, here's some of the test reactors compared to a human being. These get referenced in the primary literature because they're the few examples of actual working nuclear rocket engines that we have good documentation of. The Russians were working on nuclear rockets in parallel with the United States, but a lot of their work is still classified or lost to history. Yeah, I chose this one showing another test blast just for the caption telescopic lens photo, because no one would want to be within hundreds of meters of a test firing. Now, this is often how NERVA is depicted. You'll see this image in countless books, but this wasn't a working system. It's actually a giant wooden mock-up. I pulled this from a promotional material from the NERVA program by Corliss. It's quite, it gives a really good educational background. It was directed mostly at school kids, and anyway. So yeah, there's the wooden mock-up again in color. The ultimate goal of NERVA, of course, was Mars. And in 1968, when NERVA was at its peak, it seemed a logical outgrowth of the program. This system that you can see, basically, these were called the interplanetary propulsion modules, but they were also purposed to become interorbital shuttles between Earth orbit and the moon to support a moon base. So a variation of them is known as the nuclear lunar shuttle. Depending on the mission duration, there could be, well, as you can see in this configuration, there were 5 interplanetary propulsion modules. Some variations just have 3. It depends. Particular orbital arrangements meant that you could fly past Venus to get a quicker trip from Earth to Mars, or the same for the return journey, which provided the opportunity of dropping off payloads into the atmosphere of Venus on the way, which you can see up front here in the payload. Okay, there's a link to the motion picture, which, if anyone's interested, well worth watching.
So that ship, you would have to build that in orbit, wouldn't you?
Absolutely.
A modular ship.
And I've got a bit more about that at the end. I wanted to cover some of the other concepts before I go over it in some detail, because it's quite interesting. Werner von Braun did a massive presentation on it in 1969. One of the more infamous moments of not really reading the room. The government wasn't that keen on funding such a massive outlay for space, especially after the goal of beating the Russians to the moon had already happened. But anyway, I'll discuss that some more. So here's the interplanetary sequence. Now, after NERVA finished in 1972, various programs have referenced its work ever since. Chief amongst them was Department of Defense with the whole Strategic Defense Initiative. Basically, in-space reactors were seen as a must for high-powered energy weapons, potentially in orbit. But also they were keen on ways of getting large payloads moved around a variety of orbits, not just to one orbit in one shot. So there was a joint workshop in 1990 that brought NERVA up to date. As you can see, the original NERVA had a lower reactor chamber temperature and a lower specific impulse. So rocket performance is determined by what's called specific impulse. And basically it's the amount of thrust that one unit of weight, so whether we talk pounds or kilograms, how much thrust value that has for however many seconds. So, for example, a kilogram of chemical propulsion, of propellant, will get anywhere between 300 and 450 seconds of thrust at its own weight. Whereas the early NERVAs were promising about 850 seconds. But as reactor designs improved in the almost 20 years between this workshop and NERVA, the specific impulse that they were hoping for increased. So 10,020 seconds is roughly 10,000 meters per second exhaust velocity. So a significant improvement. But as you can see, the weight of the reactor, including the shielding and the engines, is roughly constant over time. One of the biggest criticisms of nuclear propulsion is the weight of the radioactive shielding. Sorry, My wife has just called to ask me how it's going. She needs a message her back. Okay. So yeah, and you can see the figure of merit down here, the thrust to weight ratio. Nuclear reactors or nuclear propulsion systems generally barely lift themselves against gravity, and thus no one can seriously consider them for launching into orbit from the surface. Probably not a bad thing. So it's always good to compare options. So this table from the same study compared a purely chemical system based on liquid oxygen, liquid hydrogen propulsion against a nuclear fission system, which was an updated NERVA. So you'll notice that basically the propellant mass is very large for chemical rockets, as you'd expect. But the tank required to hold the hydrogen alone is much larger than the corresponding volume for the chemical propulsion system. The reason for that is that hydrogen is irritatingly much less dense than water. So it's usually just over 70 kilograms per cubic meter versus liquid oxygen, which is denser than water. So yeah, in the end, I derived some of the figures at the end. You'll see that the tankage, which is for a chemical system, 4%, which is something that the space shuttle external tanks achieved. And whereas for pure liquid hydrogen, it's something like 17%. And this has implications on the kind of missions that you can achieve. I've discussed those implications in several of my blog posts. So what happens when we go to other planets? And liquid hydrogen is in shorter supply. Okay, so Robert Zubrin studied this proposal in the early 90s, and basically he's looked at what we could access on the surface of Mars. I'll come back to the nice artwork in a moment. So the options are CO2, which you can pump straight out of the atmosphere, water, which as we know now can be found under the surface just about anywhere except around the equator, and then what can be made from CO2 with a bit of hydrogen is methane, or you can separate out the small fractions of other gases. And Zubrin works out possibly the best performer, because there's so much of it and so easy to access, is actually the CO2. Because annoyingly, water ice is difficult to get up to a easy temperature to handle. Now, one thing with using a purely hydrogen propulsion system is that making pure hydrogen is difficult if you don't have a source. So separating it from water by, say, electrolysis or high temperature chemical reactions generally takes about over 12 megajoules per kilogram. But what that doesn't factor in is the fact that if you're sourcing it from water, you're basically using only 1/9 of the mass of your supply. So, and once that's factored in, it's something like 120 megajoules per kilogram. So if you don't have a handy supply of hydrogen, like we do on Earth, then the performance value of a solid core nuclear propulsion system is questionable. And that's where we get into something with a bit higher performance. But Mars, we could access using nuclear rockets using the local materials. It allows you to move around on the surface. And yeah, it's a good concept, although presently no one's really studying it. There's some more figures from Zubrin's papers. Now, a quick stop before I get into higher energy systems is the low pressure nuclear thermal rocket, which was also discussed in the NASA DOE workshop. It's a concept which improves performance by cheating with the chemistry of hydrogen. So you run the reactor hot enough, hydrogen molecules start breaking in half, and the more hydrogen atoms that you have, the higher your resulting specific impulse. As high as you can see, 13 kilometers per second, which is decent performance, so long as you have a good supply of hydrogen. So, beyond solid core reactors, some pretty pictures along the way. So updated from NERVA, this is pretty standard configuration for a lot of NASA concepts that have been studied over the last 20-something years. As you can see, giant hydrogen tanks, a cluster of roughly 4 nuclear rocket engines, a long way from the habitat at the front. And there's a view from the side of the same configuration. The journals are full of concepts like this. The basic upshot of the NERVA program was that they have a very good idea of how to build fairly small nuclear rocket engines. So you cluster them to push fairly large payloads, most of which is hydrogen propellant. For higher performance, things have to get extreme. And this is where fiction once again intrudes. Hopefully most of the audience recognize this spaceship. It's the Discovery from 2001 Space Odyssey. Because of its lack of giant radiators, which space nerds have complained about for the last 50 years, several people have decided that it must use a gaseous core nuclear reactor, which is the next denizen of all things nuclear that we're going to look at. So uranium can only get so hot before it starts melting and before it gets too weak and starts basically the hotter it is, the weaker it is mechanically. With high pressure hydrogen blowing through it, bits of reactor are going to go blasting out your rocket engine. So instead of trying for a solid core, nuclear engineers have said, well, why don't we make it a feature rather than a flaw? Instead of trying to keep the core cool, let's get it super hot. So what happens? Well, you go to the liquid core, which is good to about 5,000 degrees Kelvin. It improves performance a little bit, but it does pose an interesting handling issue of what do you do with liquid uranium. So because nuclear engineers have had a lot of experience with uranium in a gaseous form, specifically uranium fluorides, many have suggested the concept of the gas core nuclear reactor. And as bizarre as it sounds, it was a seriously studied concept. Its temperature is, well, hotter than the sun. Some designs had basically a uranium plasma at something like 55,000 degrees Kelvin, or for old school engineers, 100,000 Rankine. And yeah, it's a design concept that has received a lot of attention. Now, there's two options. One is you let some of the fissioning uranium plasma get vented with the propellant, and this is called an open cycle gas core reactor. Of course, you don't want to waste your fuel, so to minimize how much gets ejected, all sorts of vortex concepts have been explored, which basically spin coolant gas around the ball of uranium plasma and hold it in place. Other concepts have feature magnetic fields to hold it there. But yeah, it seems messy and probably not something that will be experimented with until we have facilities in outer space. So I'll move on from the open core system to the closed cycle, or what's otherwise known as the nuclear light bulb. One of the amazing things which the nuclear engineers discovered in the 60s was that quartz glass is actually incredibly transparent to ultraviolet light at certain frequencies, the kind of frequencies which hot uranium plasma will be emitting. So they came up with the concept of wrapping the fissioning core in glass and then using a mix of hydrogen and neon gas to keep it in place, but also a cooling system where your propellant, so separate hydrogen feed, goes around the light bulb and stops it from exploding from its own internal pressure as the fission process increases in power. So yeah, what's on screen now is one of the reference concepts. Its performance was, they felt confident that they could get at least 1,870 seconds of specific impulse which is a bit over 18 kilometers per second. But the upper limit is a bit less defined. So what they looked at and what they figured out was that you could push the gas core reactor to something like 7,000 seconds of specific impulse, which means roughly a jet speed of 70 kilometers per second. And this would enable all sorts of missions. Unfortunately, the downside is that because the power levels are so extreme, very large radiators to handle the waste heat load have to be utilized. So, and this wasn't just paper studies. As you can see in these pictures, they actually worked on the light bulbs, creating the containment systems for fissioning uranium plasma. There's a system flow diagram. So lots of detail went into the concepts. Then you have your performance range. They were fairly sure they could get away without a reactor up to about 2,500 seconds specific impulse. Oh, yeah, so no radiator up to that point, and then after that, you have to include a radiator. As you can see, the fuel radiating temperature gets extreme the higher you go. But, you know, 2,500 seconds specific impulse allows fast missions to Mars and missions to the moons of Jupiter and Saturn, as well as the asteroids. Before the test program ran out of money, they were starting to build test units. So they weren't working rockets as such. They were more engineering systems to determine what was required to contain burning plasma of uranium. The source report that I got this from, it was a rather coarse black and white picture, so apologies. But yeah, this is one of the systems that they were had made good progress on. So yeah, some more performance characteristics for the systems, like quite amazing compared to chemical rockets, but quite extreme as well. The temperature of the plasmas was just, yeah, incredible, as well as the operating pressures. So we're talking hundreds of atmospheres. And the thing to remember with a light bulb is that the glass itself is very thin, and it's only kept together by the equality of pressure between the exploding plasma on the inside and the flow of coolant hydrogen gas around it. So yeah, any minor imbalance could fracture the light bulb and result in hot plasma blowing through the engine. But they were fairly bullish about being able to control it. So, and there's some uranium plasma for real in one of the pictures from that same paper. It'd be good to get some color pictures of something rather, well, terrifying, considering the possibility of how much radiation would be involved. A recent study, well, recent in the sense of the last 30 years, looked at some options on Mars missions, getting decidedly better performance than solid core or chemical rocket systems. But yeah, so if gas core rockets weren't crazy enough, there's a couple more options that were crazier. One of the more recent concepts, also by Robert Zubrin, is the nuclear saltwater rocket. Now, by salt water, it's uranium bromide salts dissolved in water, but kept in tubes so that the fuel is subcritical until it gets mixed. And as the diagram indicates, there's a detonation point. So it's no longer a controlled fission reaction. The only control is the flow rate of fuel into the engine. But the promise of the concept is that it creates high energy and high thrust. Although exactly how well or how the safety of such a thing could be managed, yeah, is an exercise that Zubrin left for the reader to figure out. The final concept that I wanted to visit was Project Orion. There's a lot of detail available. I'll stop sharing my screen, and because I want to show you. Okay, so I very much recommend this reference. Although, sorry, it's back to front. Project Orion by George Dyson, who's the son of Freeman Dyson, the late physicist, who basically was one of the brains behind Project Orion.
Adam, we're going to have to wrap it up in about 5 minutes.
Oh God, did I really go that much longer than I? Oh, well, that's all right, because I'm actually I was hoping that I could cover Orion in more detail, like on a future occasion, hopefully with better control over my display.
Show the video of Orion. They got to see it. It's crazy.
Yeah. So yeah, I'd love to talk about Orion and some related concepts, some of which I've been involved in. So yeah, I'm happy to wrap now, and I'll get some pretty pictures together for a big Orion display. So, any questions?
Are any of these currently under development? Are they continuing to develop these engines?
Yeah, well, that's the whole point of the NASA DARPA collaboration. Aerojet Rocketdyne was involved in the early days of the nuclear program, and they've kept work going, ticking along, basically, because I think they just want to, you know, maintain the skills, because there was a lot of engineering know-how that went into these systems. So at a low level, there is still activity, and now that there's been renewed interest in applying nuclear energy to propulsion, you might see a ramp up in those programs.
So one of the things you showed there was a Earth orbit to Moon transit system using those engines. If you used nuclear engines in the Earth-Moon system for decades, would you pollute that environment? Would you have a buildup of guck that you don't really want?
Well, that's a really good question, and I threw some links in. So a resource which covers a lot of these issues is Winchell Chung's Atomic Rockets page, which is a massive compendium of real and fictional concepts. And he provides some of the discussions from the 60s that people looked at about, because the one thing with NERVA and basically any reactor system is that once the reactor is activated, it's incredibly radioactive. So a big part of the mass of that system is the radiation shield, so that other ship components and the crew don't get a lethal dose. So as for what happens to the exhaust products, so a solid core reactor shouldn't bleed radioactive material into the jet, or at least that's hoped. There will always be some material escape, and likely because it is ions, especially after nuclear fission. So, and I'm talking about fission products. So when uranium is split apart, you get two new elements. And the elements that are produced are fairly well known. And some of those like decay very quickly. So they don't build up over time. Like a lot of the issues with nuclear waste aren't due to fission products, but are actually due to the transuranic elements that get created when a reactor is operating. So those heavier elements will remain as part of the reactor. So it's only the lighter fission products that will escape. And so in the Earth's magnetic fields, there is a distinct possibility that you could get ions building up. But the actual number of them is, it would take a bit of dedicated study to figure it out. But those belts, those radiation belts around the Earth are called radiation belts for a reason. They're already full of high energy protons and atomic nuclei created by the sun and cosmic rays that are hitting the Earth's atmosphere all the time. In fact,
we've got to wrap it up, Adam. It's 9:30 here. So everybody, let's thank Adam and
thank
you very much.
I hope I didn't bore anyone.
Okay, we meet at the, some of us meet at the Red Coat Tavern after this. So if you want to eat, they stop taking orders soon. Laura Wade is hosting the discussion group on the 28th. We will be sending out an email about that. And it's in the WASP, and our next meeting is in person at Macomb. What do you have there, Laura? Oh, it's on. Okay, it's in the WASP. Go home, everyone. Good night. Thank you very much, Adam. Alrighty. So.